Okay, good morning, class. This will be our last chapter for this course, chapter 7 Beyond NoSQL. This one also a bit short chapter, consists of 5 subtopics. At the end of this lecture, you'll be able to understand the alternative data storage paradigm beyond NoSQL, identify use cases where this paradigm outperform the traditional database, and compare contrast these approaches with NoSQL and relational database. And lastly, appreciate the diversity of tools. What is a file system? A file system is one of the oldest and most fundamental ways of organizing and storing data. Think of your computer's hard drive. Okay, it's organized files and folders in hierarchical structure, while file systems are not databases per se. They can serve as a simple and effective way to store unstructured or semi-structured data. How does it work? Files are stored in directories, folders, and subdirectories, subfolders, and each file has metadata, name, size, creation date, and so on and so forth. So the file system does not don't enforce schemas or relationship between files. Okay, this is the whole file system that we have come across. So the use cases like media storage, storing image, videos, and audio files where relationship between the data points are a critical thing. Backup system, archiving data for disaster recovery. Log file storing application logs in plain text file. Okay. Pros and cons of file system. It's very simple and easy to implement, and no need for complex setup and maintenance. Scalable for certain types of data like media file. The cons: lack of querying capability, because we cannot query in order to get the data, retrieve the data. Poor performance for large scale structured data, so no built-in mechanism for consistency or concurrencies. The real-world example, Amazon S3 Simple Storage Service, is essentially a cloud-based file system designed for storing massive amounts of unstructured data. It's widely used for backup, media hosting, and static website storage. Number 2, event sourcing. What is an event sourcing? Event sourcing is a paradigm where instead of storing the current state of an entity, you store a sequence of events that describe how the entity reached its current state. It's like keeping the detailed journal of everything that happens to your data. How does it work? Every change to the system is recorded as an immutable event. Immutable event means which cannot be modified. The current state is derived by replaying all past events, and events are typically stored in an append-only log. So the use cases here, like audit trail. Okay, we can do undo and redo functionality applications that need to revert the previous states. Real-time analytics. Pros and cons for this. The pros are: full history of changes is preserved, okay, and enables powerful features like time travel and replay. Highly scalable for heavy workload. However, there are some cons there. Complex to implement and maintain. Querying can be challenging without additional tools and requires significant storage for large volumes of events. So the real world examples, you can see event sourcing is a commonly used banking system. For instance, when you transfer money, the system records the event transfer of $100 to an account B rather than just updating the account balances. Okay, this ensures transparency and traceability. This is the keyword, transparency and traceability. So you're able to trace who transfer the money, when they transfer the money, and all these details. Memory image. What is a memory image? In a memory image architecture, the entire state of an application is kept in memory rather than on a disk. Periodic snapshots of the states are saved to persistent storage for recovery purposes. How does it work? All data resides in our RAM for fast access. Okay, a random access memory, RAM. ROM is different. Okay, read-only memory. So changes are applied directly Two, the in-memory state, and snapshots are taken at regular interval to prevent data loss. Use cases, for example, high performance application like trading platforms, gaming servers, and real-time simulations, prototyping, quick development cycles, where persistence is secondary. Pros and cons. Pros are blazing fast read-write speed since the data is accessed directly from the memory. When the data is in the RAM, so you can directly access. So there's a speed wise is very fast. Simplify programming because there is no need for database queries. However, the cons are limited scalability, risk of data loss are very high, and then not suitable for application requiring long-term storage. The real world example on this, many multiplayer online games use memory images to manage player states during gameplay. So the game server keeps all players' information in the memory for quick update and only writes periodic saves to disk. So which means the old data will be saved to the disk, and the most recent one will be in the memory for the past access. Version control. While traditionally used for source code management, version control system can also be applied to data management. With this system, track changes to files over time, allowing user to revert to earlier version if needed. How does it work? Changes to the file are committed. Committed means saved with timestamps and metadata, and branches allow parallel development of different versions. Merging combines changes from multiple branches also. So when we modify one file to another file, so one from version 1 to version 2, version 2 to version 3, so we try to save that file as a in a version, so that could be useful. Use cases, collaborative editing, configuration management, and data governance. The pros and cons: excellent for tracking changes and collaboration, provides a clear audit trail because we have multiple versions there. So support branching and merging for experimentation. Cons: not optimized for very large binary files, okay, which means the scalability is not that very large. Can become unwieldy with extremely high frequency changes because of the data growth. So Git is the most popular version control. While primarily used for code, it's increasingly being adopted for managing small to medium sized data sets and configuration files in data science workflows. And the last one is XML database. What is an XML database? XML database stores data in XML format, extensible markup language, which is both human readable and machine readable. Unlike a relational database, XML database are schemaless and hierarchical. This is what most of the NoSQL is using. The data stored as the XML document, queries are performed. We can do query performance, and relationship between elements are expressed through nesting. So which means nesting, right? A inside B, inside C, inside N. So there is a nested expressions. Use cases: document-centric application like legal documents, scientific papers, e-books. Interoperability: exchanging data between systems with varying schemas, and metadata management, storing metadata about multimedia files. The pros: flexible schema, okay, ideal for semi-structured and hierarchical data, widely supported across platforms. While cons: slower than the binary format for large data set, obviously, okay, when you have a large data set, it's slow. Verbose syntax increases storage requirements and limited adoption compared to JSON-based solutions. MongoDB using JSON-based, they still can use XML also. So MarkLogic is a popular XML database used in industries like publishing and healthcare for managing complex hierarchical documents. As a summary, we have learned file system, event sourcing, memory image, version control, XML databases. So hope you guys can understand. in order to test your understanding, I will give an assessment question activity in author. So kindly do it after watching the video and submit. Thank you.